Good evening, everyone. Welcome to the last live discussion session on geology and soil mechanics. So today is our 12th week discussion session, and so this will be the last discussion session for this course. So uh, in the last class we had solved some problems from earth pressure theories, and then we solved some problems from the chapter of stress distribution or stresses in soils, where we found out the change in stress at a certain depth in the soil when some load was applied at the surface of the soil, right? So we did that in the previous class, and in today's class what we will be doing is we will be solving um, some problems from each of the chapters. Okay, one or two problems from all the topics that we had covered, right? So we will be solving all of them one by one. Starting in the starting, we will be solving the two problems which were remaining from the previous class. One problem was two problems. Those two problems were from the chapter of the earth pressure theories. So first, we will be solving those two problems of retaining wall earth pressure theories chapter, and then we will be solving one problem from the stress in soil chapter, and then slowly we will, from the first chapter, we will be slowly solving one or two problems, mostly one problem each, so that we can wrap up the course and for this semester. And so let us begin slowly one by one. Okay, so the first problem is retaining wall with stratified backfill and surcharge load is drawn. Right. So we need to estimate the resultant thrust and its position. Okay. So I will draw the retaining wall at stratified backfill. I will draw that figure for you. And what we need to do is that we need to estimate the resultant thrust and its position. All right. So let me draw that for you first. To say this is my retaining wall. Say this is my retaining wall. We have the layers here. The top we have the surcharge load which is acting. Okay, the soil properties are given, gamma for this one, phi c is 0, gamma is 20, phi is 10 degrees, c is right, and let me mark the height. So this is 3 meter, this is 3 meter. All right. So as we can see, this is the arrangement. So two soil layers are there. The upper layer is a phi is equal to 30 degree, the lower layer is a phi equal to 10 degree, upper layer is C equal to 0, that is cohesionless soil, and the lower layer has some cohesion value which is of 10 kPa. Okay, we need to estimate the resultant thrust, and okay, so we need to estimate that. So actually we will be estimating the active thrust. All right. First, for the top soil layer. Okay, so let us first write for the top. Okay, for the top soil layer, we have Ka1 is equal to nothing but 1 minus sine 4. Is equal to 1 minus sine 30 degrees to 1 plus sine 30 degrees is equal to 1 by 3. Okay. Next, what we need to do is that we need to take into account the effect of surcharge. So due to the surcharge, what will happen? Little earth pressure will act, right? So due to the surcharge, let us write small pa1. Okay, it will nothing but 10, right? 10 into 1 by 3, right? It's equal to 3.33, isn't it? And after that we have what will be the line of action of this one? Will be h by 3. So from the bottom it will be 6 by sorry, this will be actually adding at the center, right? So it will be how much? Yeah, so it is something like this, right? So this is PA1, correct? So from the bottom if we take, so we will get y1 bar is nothing but 3 plus 3 by 2 equal to 4.5 meters. Okay, so we got for the top soil layer, right? Now we got the effect of the surcharge. Now for the top soil, let us find out the effect of the soil mass. So Pa2 is nothing but Ka1 into gamma into Z. So this variation will be something like this, right? So what is, so this, what this is Pa2 small, right? So what will be the value? 1 by 3 into gamma. What is our gamma? Gamma is 15 into, what is the depth here? It's 3 meters, so it will be 15 kilonewton per meter square. Correct. So let us calculate the PA1 capital. So it will be 3.33 into what? Into the height into 3 is equal to 3.333, 9.99 kilonewton per meter length of the wall, and PA2 will be nothing but half into 15 into 3, right? So half into area of this triangle, right? So half into 15 into 3, nothing but 22.5 kilonewton per meter, right? We got that, isn't it? Now what, let us go to the bottom soil layer, correct? So in the bottom soil layer, what we will do first, the upper layer, this upper soil layer will be acting as this upper soil layer will be acting as a surcharge to the lower soil layer. So what surcharge? Surcharge will be 10 plus 3 into 15. That much surcharge will be acting. So let us write that PA3 is nothing but, sorry, It is this electron. So Pa3 is nothing but how much? 10 plus 15 into 3. 10 plus 15 into 3 into K2. So what is our K2? 1 minus sine. How much? It was 10 degrees, right? 1 minus sine 10 degree by 1 plus sine 10 degree. K, right? 0.704. So this will be how much? 15 into 3 is 45 plus 10 55 into 0.704. 38.72 kilonewton per meter square, right? Got this Pa3. So what will be the capital Pa3? So Pa3 will be nothing but area of the rectangle into 3. 116.16 kilonewton per meter, and Y3 bar will be nothing but 3 by 2 is equal to 1.5 meters. Right, done. Now there is some cohesion in the soil also, right? So let us take into consideration, so due to the effect of cohesion, so minus 2ic root over Ka, that that term will come, right? So minus 2ic root over that term, root over Kc, Ka2, that term will come, right? Isn't it? Right? So that term is actually a fixed term, right? It doesn't depend upon the depth, isn't it? So we will consider that due to the that cohesion part, we will consider PA4 nothing but minus 2ic root over Ka2 into minus 2 into 10 into root over 0.704. So it will come minus 16.78 kilometers. So PA4 will be area of this rectangle, right? So it will be how much? Into 3. So minus 50.34. So minus 16.78 into 3. That's 50.34 kilonewton per meter. So got PA4. So Y4 bar will be nothing but 1.5 meters. Right? So 2%. Third part is the effect of the soil mass that varies with our depth. It's anyway Ka2 gamma to Z, right? So let us write that. So PA, how much PA5, I guess? Yeah, PA5 is equal to K2 gamma 2 into Z. So nothing but 0.704 into gamma is how much? Gamma for the bottom layer is actually 20, and there is 3. So 0.4 into 20 into 3, 42.24 kilonewton per meter square. So area capital PA5 will be nothing but area. So half into 42.24 into the height 3. 5 to 3, nothing but 63.36. 63.36. Okay, so we got PA5 and it's acting at 3 by 3, so 1 meter, right? 1 meter from the base, right? So total PA is nothing but summation of PAI by I goes to 1 to 5. So if we add all these things, 10 plus 22.5, yeah, where is it? So 9.99 plus almost 10, 10 plus 22.5 plus 16.16 minus 50.13, 15.3, 50.34 plus 63.36. We get the total as 161.66 kilometer. Okay, kindly check all these values by yourself. Correct. So and the line of action will be nothing but summation I equal to 1 to 5 PAI into I bar I by capital PA. So this will actually give you 1.84 meter from the base. Okay, so we have the wall. So resultant PA is acting at a height of 1.84 meter from the base. Correct. So done. So we have solved this problem. Let us go to the next problem. Next problem is a section of a cantilever retaining wall is drawn below. Find the factor of safety in sliding. Okay, in sliding, overturning, and bearing. Okay. Okay, actually, it's all data. Okay. Okay, so let us try to solve this. Okay, let us see how much can we solve this. If some theta is missing, we'll solve. So let me just draw the retaining wall for you once. Huh? This is the cantilever retaining wall. Here we have this a charge acting of 35 kilonewton per meter square, and this is actually 0.4 meters. This is 0.5 meter. This base width is 3.5 meters. This height is 6 meters. Okay, correct. And this soil is actually a soil, so this part is 2 meters. Correct. And also the soil properties are given. My C dash is 0, my phi is 41 degrees, gamma is 16 kilonewton per meter cube. Okay, so these values are given also. Yeah, okay, yeah. So uni okay, also SBC, safe bearing capacity of the soil below, it means the soil here, right? The safe bearing capacity of the soil is 200 kilonewton. Okay. So first for phi is equal to 41 degrees, what is our Ka? Nothing but 0.2077. Okay. So this is our phi dash Ka value, right? Now, okay. So what we will be doing is that we will be actually considering our Rankine's theory. So what will be our PA value? PA will be nothing but K into Z plus 35, which is our Q, right, into K, isn't it? So, sorry, extremely sorry. It will be K into gamma into Z plus Q. right? What is our K? 0.2077. What is the gamma value? Gamma is 16. What is Z value? Total 6 meters, right? So yeah, 6 meters plus our Q. What is Q? Q is 35. So we got this. Pressure is 16 to 6 plus 5. 27 point. Yeah, 20. Sorry. So 27.21 kilonewton per meter square. So we have 5 plus. Okay, 27.21 got, right? So now at what point? So this will actually this. So let us now find a capital P. Okay, so we will be following Rankine's theory. Remember that, right? We will be following Rankine's theory, and we will be assuming that our wall is smooth. All right. So our wall is smooth. We will be considering that. So what is capital PA? Capital PA will be, see, there is some Q part, there is some P, this part, right? So like the previous problem, there is the Q part and there is one triangular variation, right? So what will be the total area of this? It will be nothing but 30. So how we can do that is you can do 35 into 0.2077 into the height is 6 meters is 43.61 617 plus half into Ka into gamma into height squared. 59.8176 to 59.817. So it will be 43.617 plus 50.7 103.43 kilonewton per meter. Okay, so let us just draw this one. So I will just minimize this thing and draw here, right? So you have this part and also you have this part, right? So this value is nothing but what? K into Q. So 0.2077 into Q, nothing but 7.27 kilonewton per meter square, and this value is nothing but 0.2077 into 16 into 6 is nothing but 19.94 kilonewton per meter square. But now if you take the areas, so let's say this one is P1, this one is say P2, right? So my P1 is how much? 7.27 into 6, so 43.62 this one, and my P2 is half into 4 into 6, 59.82 to 59.82, this much, right? Okay, so we got that, right? So now what we will be doing is that, so we got this. Now yeah, now what we will be doing is that we will be determining the distance, okay, distance of the base reaction from the heel, right? So we will be determining the base reaction from the heel, so we will be taking all the moments of the forces about the heel, right? So let us just write the table here. So force, okay, force, so we write here force kilonewton, moment arm meter, and we have moment kilonewton meter. Okay, the first four is our P1 is 43.47. So moment arm is what? Moment arm, it is at 3 meters. So 3 meters here. Here this is acting at 3 meters from the bottom to here. It will be 3 meters, and for this one it will be how much? 3 by 3, 6 by 2, 3 meters, and this one will be 6 by 3, 2 meters, right? Moment arm will be 3 meters. 3 meter will be 130.4. The next one at 59.82. This is P2, 2 meters. Correct. Okay, so now what is the weight of the stem? Weight of the stem means this portion, right? The weight of this, nothing but so what is the unit weight of concrete? It's 24 kilonewton per meter cube, right? 24 kilonewton per meter cube. So 24 weight of the stem is equal to what? 24 into what is the height? What is the height of the stem? 6 minus 0.5, so 5.5. So from here we are measuring, right? So 6 minus 0.5, 5.5 into the width was how much? It's given 0.4, so we get it as 52.8. So the moment term is that will be 2.2 from the hill. All right, okay, so just a second. Okay, so from this point actually I'm measuring. Okay, correct. So it's nothing but 116. So weight of, similarly the weight of base, okay, weight of base is 42. This will be 1.75. This will be 73.5. So I will just continue here. Okay, here weight of backfill means this soil. Okay, this soil backfill is nothing but it is 176. It will be 1.0 more 176, and the surcharge load 70 0. Okay, now the sum of all the vertical components, okay, sum of all the vertical forces, these are our horizontal forces, okay, not that. We will consider all the sum of the vertical forces. Sum of vertical forces, so if we sum all that up, it will be 340.8 kilonewton. Okay, and all the horizontal component, It will come out as 103. So my X bar will be 38685.71, which is nothing but summation moment 1 divided by my vertical forces. So it's 2.01 meter. Just a second, give me 1 second. Okay, I'll see that later. Okay, so eccentricity we find out next. Meters. Okay, next we have the maximum and minimum base pressures. So Q max is nothing but RV by P 1 plus C by P. So it will give me 340.8 by 3.5. Okay, so you can say that see that minimum is positive and Q max is our less than our SPC. This is less than SPC and this is positive. So okay, correct. So this should be positive Q minimum because our soil cannot take tension, so it cannot be negative. Now factor of safety in sliding. Equal to RP 10 delta dash RD. So this is the friction angle between base soil and base of retaining one given as 2 by 3 of pi. Okay, so take 340.8 and 7, it's greater than 1.6. So okay, all right, so we determined all these things, correct? Okay, just give me 1 second. Just give me a second. Okay. Just be back. Okay, so let's move to the next problem. Yeah, so the next problem, we have a rectangular loaded area 6 meter times 7.5 meters that carries a load of 20 kPa. We need to determine the vertical stress at a point P located outside the depth of 7.5 meters. Okay, so let us see how the figure is actually. We'll draw the load area for you. Okay, so we need to determine the vertical stress at this point P. All right, so and this point P is actually located at a depth of 7.5 meters. All right, and this is our loaded area. So as you can see, the P point is actually situated outside the loaded area. Okay, so how can we solve this? So in order to find this out, what we will do is that we will be drawing some fictitious some fictitious loading. Okay, so we'll be drawing some fictitious loading, and then using that we will be determining the pressure under this P. So let us draw that, right? So this thing, what we will be doing is that we will be converting to something like this. So this is our loaded area. So we will be drawing some more areas here. Okay, so our P point is here. So this much, it's 7.5 meter. This much will be 3 meter. Okay, this much is 1.5 meter. This much is 6 meters. Okay, let us name these areas. Let us name it A1, 3, A2, and A4. Okay, so these A3, A4, A2, these are our fictitious areas. Okay, so what we will be doing, that we will be determining the factor K for all, and we will be actually subtracting these factors which we calculate for A2, A4, and A3. Okay, and we will be adding the one for A1. Okay, okay, so let's just name this A, D, E, F, G, C, H, P. Okay, so my sigma z, which is the increase in stress, will be equal to K A just A H E P H K A E P H minus K B F P H B F P H minus K D E P G. It is DEPG, this one, plus we will be adding this small, because we have deducted this 2 times, so we will be adding that small part, LFPG or LCFPG. Okay, this one is A4, this times 200. Okay, this will give a increase in stress. So for 4 times, what we need to do, you need to find out this K value. So it's a little bit lengthy problem, right? Because you know this K formula is really big. Say you don't have the table with you, then you need to use this formula. So this is our formula. So let us find that out for at least one or two. Okay, rest you can do that later. So for area, let us do it for AEPH. So AEPH is which one? So so you can see here AEPH. So here L is what? 7.5 plus 3. So 10.5 meters. L and your Z is L is this much and your B is 7.5 meters. This is 6 plus 1.5. So and your Z depth is given as 7.5 meters. So you can find out our M and N. M is nothing but L by Z. Nothing but 10.5 by Z. 5. And N is P by Z. 5. Okay. So now let us put this M and N values in the equation for K. For that, last class I told you that you just find these values first. Mn, then m square plus n square. Okay, you find these values first so that it will be actually easier. So this Mn is 1.40 to 1.4, and m square plus n square is how much? M square plus n square is 0.96. Okay, then we can put in this k relation. So 2 into 1.4 into 2.96 plus 1 by 2.96 plus 1.4 square plus 1, 2.96 plus 2, 2.96 plus 1, tan inverse 2 into 1.4, 2.96 plus 1, 2.96 minus 1.4 square plus 1. So let us see 1 by 4 pi. How much this much is coming? 0.178 plus tan inverse 2 into 14 into 3.96. So 87.89 pi by 180 to pi by radians we need to find this out. Right, so it will be by 4 pi into it will be close to 0.2. Okay, it will be about 0.2. So we got this for APH area, right? So K connect to KAEPH. Similarly, what we can do, you can find out for other areas, say BFPH. So BFPH. So KPF. Here M is equal to L by Z. So what is the L for BFPH? Can you just see and tell me for BFPH how much is the L? BFPH, what is the L? Yeah, and what is this one? B 1.5, right? Uh, so 10.5 by 7.5, same 1.4, and N is your B by Z 0.5 by 7.5, 0.0. Okay, so again let us find out Mn and M square plus N square. So Mn is 1.4 into 0.2, it's 0.28, and M square plus N square is 1.4 square plus 0.2 square. 2, right? So again we will put it in this the relation. We'll get 2 into 0.28 into square means 3 root over 3 by 3 plus 0.28 square into m square plus n square. 2 is 4 by 3 plus tan inverse 2 into 0.28 into 3 over 3 minus 0.28 square. Point 4. To just answer is not matching 2 into okay 132, right? 142 plus 132 by 4, so it will lead to 0.058. Okay, so similarly what we can do is we can find out other case. So for area DEPG, M is 7.5, 7.5, 1 is 3 by 7.5, which is 0.4. So if we do that, we will get the KS 3 and CEPG. Okay, so finally my gamma z will sigma z will be 0.2 minus 0.058 minus 0.1013 plus 0.0328. Sorry, into 200 will be equal to how much is it coming? 0.2 down to 14. How much? 32. How so much? Should come around 13, 14 like that only. Zero point 0.2 minus 0.058 minus 0.1013 plus 0.0328. Yeah, 0.0737. This is 35 200. Okay. Okay. So let us now move to the other problems. The plastic limit and liquid limit of a soil are 30% and 42%. So we are just moving to the first chapter, that was our index properties and soil properties, that chapter. Okay, so the plastic limit and liquid limit of a soil are given 30% and 42%. The volume change from the liquid limit to the dry state is 35% of the dry volume. Similarly, volume change from plastic limit to dry state is 22% of the dry volume. Going to determine the shrinkage limit and the shrinkage ratio. So let me first draw our this chart. So do you remember all the names of the three limits? So this is water content and this is a volume here. So what was this limit called here? Yeah, it was liquid limit, and then after that this is plastic limit, and this is what, this one, shrinkage limit. Okay, so this one is what, this one is how much, this one is a dry volume. So you know that as we cross the shrinkage limit in the backwards direction, here the water content is 0, so this is a dry volume. So here to here the volume remains constant. Okay, so here till here it's totally saturated, and here it becomes completely dry. Okay, so this we can see, so write this at the volume at plastic limit, and this we can write as the volume at liquid limit. All right, so this much is nothing but VL minus VD, right? And this much is nothing but, sorry, not this one. And this one is VL minus VP. Okay. So now it is given in the question, the plastic limit and liquid limit of the soil are 30% and 42%. So W plastic limit is 0.3 and my liquid limit is 0.4. Okay, so from this we can write that our VL minus VD. Okay, so it's given that the percent volume change from liquid limit to dry state is 35% of the dry volume. Means the volume change here from liquid limit to the dry state is 0.35 times the 35% of the dry volume. So VL minus VT is 0.35 times VT. And the volume change from the plastic limit, okay, from the plastic limit to dry state. So plastic limit minus dry state is 22% of the dry volume. Okay, so this much is given given in the question. Now, how to find this shrinkage limit? How can we find that? So what we will be doing is that we will be just interpolating, okay, or taking the slope of this graph. Okay, from there what we will be doing is that we will be finding the shrinkage limit. So let us take the slope. So if you take the slope, we'll have WVL minus VP by WL minus WP is equal to VL minus VT by 0, sorry, let's write next, by WL minus WS. Okay, so we are just taking the slope, right? Okay, so this angle and this angle, so this we are considering this triangle and this triangle. Okay, these two we are considering. So we can write this part, right? We can write this part. So next let us just put the values. So VL minus VP, you can write this as 1.35 VT minus 1.22 VT. So what we are doing is that we are just representing VL and VP in terms of VD. Okay, so VL is this side, that side it will go, so 1.35, VP is 1.22 VD. Okay, from the given conditions we are writing, and WL is given, and this is also given. Next we have 1.35 50 50 0.42 is given. This is our WS is our unknown. So now if we do the arithmetic operations, we get this 0.1235 50. So we have WS. From here you can write. So please find out WS. Okay, from here this is minus. So 0.35 VD, 0.35 VD. So this one is 1.3. Sorry, extremely sorry. So VD cancelled, and then we have how much? 0.13 divided by 0.12, 0.09, 0.32. So this is 0.42 minus 0.323. 0.42 minus 0.323 give us answer nothing but 9.7%. Okay, this much is done. So we determine the shrinkage limit. So the next task is to determine the shrinkage ratio. So this is the relation for formula for the shrinkage ratio. So the VL is 1.35 VT minus 2 VT. I try. So it's percent. We are using percent sign above, so we directly put this in percent only. 42 minus Okay, so please calculate this shrinkage ratio. How much is it coming? It's 1.08. Okay, so we have solved it. Now let us go to the next problem. Yeah. So our soil, this is from the soil classification chapter, right? So in the soil classification chapter, we studied how to classify the soils. So the main broad classification was gravel, sand, and then clay or silt, right? So first, more than 4.75 mm, if the size is more than 4.75 mm, then it's gravel. Then between 4.75 mm and 75 micron, that is our sand fraction, and less than 75 micron size is our clay fraction, right? Right. So we studied the Indian standard soil classification system, the ISCS soil classification system, and we saw that how we can classify any type of soil. So why do we classify soils? So soil classification actually enables us to at a first glance, it enables us to identify the property, like the probable properties of the strength of the soil, and also you can guess about the strength of the soil somewhat, not that much actually, but just you can actually say, like you can just guess how the soil might behave. So that's why soil classification is actually very important, right? So uh, so there are two types of so how do we classify the soil? We actually first we have to, what we have to do, we have to sieve the soil, right? So sieving is the process. So wet sieve analysis and dry sieve analysis, both things, both stuff are there. So what we need to do is that we need to do the dry sieve first, and if there is a considerable amount of clay fraction, that is then we need to do the wet sieve analysis too, followed by our hydrometer analysis, right? So after doing this CU analysis, what we do, we can draw our grain size distribution chart. From the grain size distribution chart, we will get uh, we will get an understanding of how is the grain size, how much amount of how much what fraction of grain sizes are present in the soil, amount of soil that we have tested. And from there, using the grain size distribution chart, also we can classify our coarse grained soil such as sand by finding out properties such as Cu and Cc, coefficient of curvature and coefficient of uniformity. Those things we can find out, and we can use them to classify our coarse grained soils. Okay. And also what we can do is, after we have done the sieve analysis, then what we do, if the fine fraction is considerable, we do the liquid limit and plastic limit test in the 45 micron 0.45 mm passing sieve. We do that, and we find out the liquid limit and plastic limit. And from the liquid limit and plastic limit, what it does is that we can actually classify our fine grained soils. So it can be clay or silt, right? It can be low plastic, intermediate plastic, or high plastic, right? Cl, Ci, or Ch, or in same in terms of silt, that is M. Also we sometimes there are cases where we have dual classification. Okay, like you might have dual classification, it can be both the terms can be in terms of fine fraction, like a CLML, or first part can be say in terms of our uh, uh, this in terms of the coarse fraction, and the second part can be in terms of clay fraction, right? Like such as say uh, GC, so clay gravel, like that, right? We had studied all those things. So we studied the various percentages between which, if there is, it is there, we need to use dual classification, and something above then other classification, something below that percentage. So 5 to 12%, I guess, dual classification. Below 5% only gravel, say it will be coarse classification. Above 12% it will be like that. Like that, many things were there. We had to like studied all those things. Right. So now let us just for revision, let us just solve this problem. So the soil has the following properties: liquid limit is given, plastic limit is given, and the passing through 4.75 micron mmCv is given. Passing through fraction passing through 75 mmC is given. So what type of soil is it? Is it a coarse soil or is it a fine soil? Yeah, fine, because more than 50% is passing through 75 micron C, right? 58% is passing, so it is a fine fraction, right? So then what we need to do is that we need to first what we will do is determine the plasticity index, right? So what is the plasticity index? PL, it is 10%. Okay, this is my plasticity index. Now what we will be doing is that we had studied a line, right? There was at a line. So what was the equation of the a line? So pi from a line, it will be, what was the equation? 0.73 20. Okay, so 0.73, liquid limit is how much? 40. So how much is it? 4.6. Okay, 10.6. So this, so our soil is actually where, above or below? It is below the line, right? It is below the line. So if the soil is below the line, what is it? Is it clay or silt? Silt. So it is silt, so it will be M. And what will be the second part, suffix of it? Yeah, so our plasticity index is 10%, right? So below that, uh, what is the, this is greater than 10%, so a line is above that, it is below that, so it will be M. And what will be the suffix? Liquid, yeah, liquid limit is between 35 and 50%, so it will be I. So it will be Mi. Okay. Okay, so next problem is from the compaction chapter. So we studied the compaction chapter where we studied that if we apply some compactive efforts or some mechanical energy to the soil, what we can do is that the air voids can uh, we can like remove the air voids and make the soil more compact, right? So we had studied that thing in the compaction chapter. So we studied about the Proctor compaction test, heavy compaction test, all those things, and we saw how we can draw the this our maximum dry density, the dry density versus the water content curve. So it is nothing but a bell-shaped curve, this bed curve. So this is my density, this is my water content, and this optimum, this is known as the optimum moisture content or optimum water content, and this is known as the maximum dry density or maximum dry unit weight, right? So we studied all those things. So in this question, let us see what it is given. So it's given that during a compaction test, a soil attains the maximum dry unit weight of 18.6 kilonewton per meter cube at a water content of 15 degrees. Okay, so this MDT is given as 18.6 kilonewton per, and this ONC is given as 15%. The GS means the specific gravity of soil solid is given as 2.7. What we need to do, we need to determine the degree of saturation and air content at this maximum dry density. Okay, and also what we need to do is then we need to find the maximum theoretical density corresponding to zero air void lines. Okay, so we also studied about a concept called the zero air void line. That is a theoretical concept where if perfectly if all voids are eliminated, right? So at that time that will give us the zero air void line, right? So first what we need to do is that let us first determine the saturation. How much saturated is our soil. So using that, what we will do, we can determine the uh, first we will determine this area degree of saturation, and from the degree of saturation, what we can do, we can determine the air content, right? So can you recall what was the formula for dry density, if you can recall? Normal general formula, what was that? G into gamma W divided by, so if you can recall the this formula or the relation between the dry density and our gamma and our void ratio was nothing but G gamma W by 1 plus C, right? So this E, what we can write, we can write down W G by S, right? So if S is equal to 1, then we get the we get what, the maximum theoretical dry density, right? Get that if S is equal to 1, isn't it? And if S is generally what, S is actually less than 1. Okay, so if S is equal to 1, we get the theoretical maximum value of dry density. So this is given as 18.6 is equal to 2.7 So what we need to do is that from here you need to find out the value of S. 95%, 0.955 or 95.5%. Okay, so this is our actual saturation, right? So now what we will do is that what we can do, we can find out the air content. The air content is what? Volume of air by volume of voids. And what is the saturation? Volume of water by volume of voids. So it's nothing but 1 minus S is equal to 0.045 is equal to 4.5%. So this much is the air content at the maximum dry density. Okay. Now what we need to do? We need to determine the maximum theoretical density compared to 0. So what will be the gamma d theoretical max? How can we find this out? 1, yeah. So G gamma W by 1 plus G. So how much will be this? 2.7 into 9.81. So please check how much it's coming. Okay, 18.8 cube. Okay, so what happens is that as we increase the water content during the test, our saturation also increases. Right, so our saturation keeps on increasing. Okay, so let us move to the next one. Okay. A layer of saturated clay 5 meter thick is overlain by sand 4 meter deep. Okay. The water table is 3 meter below the top of the top surface. The saturated unit weight of clay and sand are 18 kilonewton per meter cube and 20 kilonewton per meter cube respectively. Above the water table, the unit weight of sand is 17 kilonewton per meter cube. Calculate the effective pressures on horizontal plane at a depth of 9 meter below the ground level. What would be the increase in effective pressure at 9 meter if the soil gets saturated by capillarity up to height? Okay, so long problem, so we will solve it step by step. So this problem is basically from where? From our this effective stress chapter, right? So where we learned how to calculate the effective stress and all those things we studied, and we studied the concept of effective stress. Okay, effective stress is nothing but the stress generated at the contact area of all the soil grains, right? So one is effective stress, so one is total stress, one is pore water pressure. So our total stress is nothing but equal to the effective stress plus the pore water pressure, right? Other name of pore water pressure is also neutral stress or neutral pressure, because if the soil grain is there, it actually acts all around the soil grain. That's why it's known as a neutral stress or neutral pressure. Okay, so why is this effective stress very important to us? Because the strength of soil is because all the strength based theories or the failure theories or the theories like such as we studied the shear strength chapter where we see so the Moore Coulomb theory and all those things, they are mostly this effective stress we need to consider, because the main stress is uh, actually being mobilized at the contact forces of the soil grains. Okay, and not so we need to deduct from the total stress, we need to deduct the pore water pressure, right? Because the pore water cannot take shear stress. Only the contact of our grain to grain contact, that can only carry the shear stresses, right? Water cannot carry shear stress. Okay, so that's why this effective stress theory is very important. So what will be, so let us first solve this slowly by one, step by step. Let us first draw the diagram. Okay, okay, so there is sand, right? So say this is our clay, saturated clay, and this is my sand. Okay, so the saturated water table is 3 meter below, so, right? So water table is here, somewhere here. This is a water table, and the saturated unit weights, everything it's given. The effective pressure and depth of 9 meter below that. So here you need to actually find out the effective stress. Okay, so here we need to find out the effective stress. So first let us find out the total stress. So what will be the total stress? Seventeen into 3 plus 18 into yeah, 18 into 1, okay, plus saturated unit of clay are C. It should be 20 into 1, right? Yeah. 20. 20 into 1 plus 18 into 5. Okay. For clay it's 18, sand saturated is 20. Okay, right? So 3 into 17, 17 is this one. 20 into 1. Yeah, 20 into 1, 18 into, okay, correct. So sum it up, 17 into 3. It's 161. Now what is the pore water pressure? It will be gamma W into how much? 6. 58.86. So we have the effective stress as total stress minus pore water pressure. So minus 6, 102.14. Okay, now we need to see what will be the increase in effective pressure at 9 meter if the soil gets saturated by capillary up to height 1 meter above the water table. So now this is the capillary height. So due to the capillary rise, this part is also saturated now, right? So let us calculate the gamma total stress. So what will be the total stress? Now this part is also saturated. Yeah. So what will be the total stress from the top? Let us start from the top. Okay. Multiplying from the top. So 2 into 17. Then how much? 20. 20 into, yes. 2 into 18 plus 5 to 2. So what is the total? Yeah. 2 to 20. Thank you. Just a second. Just a second. Yeah. How much? Okay. Now comes the pore water pressure. So what is the pore water pressure? Same, right? It will be same only, 6 into gamma w. No, no, it will be 6 only. It's always calculated from the water level. Okay, it won't be 7. So only change, see, if you are asked that what is the pore water pressure here at this level, then you can say that it is minus 1 into gamma w. Okay, otherwise no change. At other points it won't be, there won't be any change. Okay, if someone asks what is the pore water pressure is this level, then previously it was 0, now it will be minus 9.81. So effective will be 0.5 square. Okay, so what is the increase in pressure? So the increase in pressure is 3 kilonewton per meter square. Okay, okay, so let us move to the next one. Yeah, so here this problem is from the permeability chapter, actually the seepage and permeability chapter. So in that chapter, what we learned the concept of seepage. So why does seepage take place? The soil is a porous medium, right? So water tends to flow from a higher head to a lower head, right? So that flow of water through this medium is actually given by which law? Darcy's law. Yeah, Darcy's law. So what Darcy's law says that our this velocity is proportional to the hydraulic gradient. Right, the velocity of flow of water through soil is actually proportional to the hydraulic gradient. So V is proportional to I is nothing but H by L. So V is equal to K into I. So this K is nothing but our coefficient of permeability. So if the coefficient of permeability is high, that means the soil is more porous, and if it is low, it means the soil is less porous. Okay, so it will resist. So we also studied, after that we studied how seepage actually affects our geostructures. Okay, we studied those things. We studied how seepage can actually lead to various problems like quicksand conditions or piping. Okay, so it causes uplift under our geotechnical structures. All those things we studied. We also saw how we can draw the flow net. Okay, we learned the concept of flow net and equipotential lines and our flow lines. We saw how we can use the flow net to calculate the amount of seepage through a geotechnical structure. Okay, we studied all those things, amount of seepage calculation. Then also we studied something called the exit gradient and all those things. Okay, okay, then we studied how to calculate the seepage through an earthen dam, right? Earthen dam using Casagrande's method and all those things. We studied all those things. And also the one of the topics that we studied was the how to find out this coefficient of permeability, right? So there are many tests, falling head test, constant head test, then this using this Packard test, right? Something like that. So we studied all those things. So this problem 8 is actually from one of the permeability tests, is nothing but the uh, falling end and the constant head test. Okay, this problem is from that topic. So also one more thing that when I studied was that when there is actually uh, we studied something called the seepage force. So we can see that when there is upward flow, what happens? The seepage force, the seepage pressure actually reduces the effective stress, right? All these things we had studied. Okay, so let us see this problem. So a permeameter of 100 millimeter diameter with a sample length of 30 centimeter was used for constant head and falling head test. So both tests, the same permeameter was used. While conducting a constant head test, the loss of head was 120 centimeter for the soil sample and the rate of flow was 3.22 uh, cc in centimeter cube per second. Okay, the rate of flow was given. Okay, so for the constant head we have the head loss, so which was 120 cm. So in 120 centimeters of head loss, the rate of flow was 3.2 centimeter cube per second. So if you need to find the coefficient of permeability. Next we have, if a falling head test was performed on the same sample. Okay, the falling head test was performed on the same sample at the same void ratio. Find the time taken for the head to fall from 98 to 50 centimeter. Okay, the die of the standpipe falling head was 20. Okay, okay. So two tests are given. The two tests were done on the same soil sample. So what we need to do is that using the data from the first test, we will be determining our answer. So first for the constant head test, let us do that. Okay. So what is the area of the sample? So what is the area of the sample? Pi into, yeah, right. This is pi by 4 into 100 square. So what is the area? Not 72.5, 7853 mm square, right? Which is 78.53 centimeters square. Okay. So and what is our hydraulic gradient? Yeah. So how much is this? What is delta H? 120 by 30. So 4. Now we have the relation Q is equal to KIA. From here what we can do is we can determine K, but Q I. Same only, na? That has come from this only, right? It has come from this only. From Q is equal to KI only, that has come. So Q is, how much is the Q? 3.22. So Q is what? Q is, capital Q is the volume and the small q is the flow, right? What is I? Area is 7, 8. So how much will it be? 3 point. 0.0102. Okay, what is the unit of Coefficient of permeability. Here everything is in cm. Okay, so it will be cm per second. Okay, and about the c, q is kia, right? So this q is nothing but q by t, k h by l a. Get k is equal to q l by h. Okay, it's coming from that only. So we got the from the now next part is our falling head test. Okay, so what is so area? So here the diameter, the dia of the standpipe is given. Okay, so let us find that. Okay, now can you recall the relation for key k for this falling head test? A upon 80 into log 1 by h2. Okay, so 2.303 into 4.909. What is L? A, capital A, 5. Yeah, and time we need to find out. Okay, and K is how much? K calculated 0.0102. Okay, from here let us get this T. Yeah, sorry, yeah. So what is H1? It's given 98 to 50. So 98 by. So how many seconds is it coming? Okay, 123. Exactly 123. Okay, so in 123.5 seconds, the head will fall from 98 to 50 for the same soil. Okay, now for the same CPA chapter, let's solve one more problem. So a 3-meter thick soil stratum has a coefficient of permeability 3 into 10 to the power minus means 10 3 into 10 to the power minus 7 meter per second. A separate test has porosity 40% and bulk unit it has 21 kilonewton per meter cube at the moisture content of 30%. Determine the head at which upward seepage will cause quicksand conditions. What is the flow required to maintain critical condition? Okay, so a 3 meters thick soil stratum is there, and the coefficient of permeability is given. So we have a porosity also given and bulk unit is also given. The moisture content of the soil is given. So from there, what we can do from this, we can actually find out the void ratio of the soil. Okay, determine the head at which upward seepage will cause quicksand condition. Okay, say say you have 3 meter this thick stratum, okay, and water table, see, say you have like this, okay, so this thick stratum is there, there's some excavation is there, and say where water table is also here, okay, so here some upward seepage might be there, due to which this water will actually try to go inside, so that will actually result in a quicksand condition. Okay, so we need to determine the head at which a seepage will cause the quicksand condition. First, first let us do the simple thing. Let us find out the void ratio. So n is given, right? Porosity is given. Porosity is by 1 plus E. So n is 0. See, from this, let us find what. Please find out E. How much? It will be 0.667, right? Uh, E. Now what we can do is that we can find out, can we find out the dry unit weight, gamma d? Can we find the dry unit weight? The bulk unit weight is given. So what was the relation between bulk unit weight, dry unit weight, and water content? Yes. So this will be 21 by 1 plus 0.31. So how much is it? 3. Okay. Now also we know that gamma T is G gamma W by 1 plus E, right? From here can we find out G? Sorry. Can we find out G from here? 2.72. 2.7. Okay. Okay. Now, can you the recall the formula for critical hydraulic gradient? Critical hydraulic gradient means the hydraulic gradient at which quicksand condition will occur, right? Means the effective stress actually will become 0. Yes, gamma d upon gamma w. So I can write I critical is equal to, no, actually it's gamma, not gamma d, gamma submerged by gamma w, right? It is gamma sub by gamma w. So it is g minus 1 by 1 plus c, not gamma dry by gamma w, it's gamma submerged by gamma w. So we already calculated G, 2.72 minus 1. E also we calculated 7. So please calculate the I critical. 1.03. Okay, 1.03. Right. Now see, now I told you that say you have a say you have something like this. You have a clay here, okay. Mm, how to show you? Okay, say you have something like this. So 3 meter clay here, and you are making a so water table is also at the top. Say, okay. Say now what you are doing is that say you are making an excavation in this. So what will happen is that due to the excavation, what will do? You will pull out the water from here. Okay. So what will happen? Water will actually try to enter from here, right? So all sides, water will try to enter. So this will actually try to actually put a upward seepage force. Due to this seepage force, the possibility is that there will be quicksand condition. So we found out that if the hydraulic gradient is actually greater than greater than or equal to 1.03, this quicksand condition will occur. Right now, what is I? I is nothing but what head hydraulic gradient I is nothing but head loss by length, right? So we can write that I is head loss by length. So from here if I put, so my head loss H will come out as 1.03 into 3. So how much it is? 3 into 1.03, 3.09 meters, right? Okay, so now what we can do, now it is asked to us that what is the this flow is some flow is there, right? So what is this value of the flow that will cause this critical hydraulic gradient? So to find out this flow, what we will do, we'll just multiply it. We'll do this operation. So K is given in the question, 3 into 10 to the power minus 7. I critical, you know, 1.034 into area. So what you can do, you can assume unit area. One. So if you do this, you will get 3.1 into 10 to the power minus 7. Just a second, it should be small q, it's right, better. Small q, meter cube per second per meter square. Okay, so the flow, this flow will actually be required to cause the quicksand conditions. And also at head of 3.09 meter, if the head of 3.09 meter is there, that will actually cause a quicksand condition. Okay, means no effective stress will be zero at that point, at that part. Okay, hydraulic gradient will be such that its effective stress will become zero. That means soil will have no strength there. So if you step over that part, you will just soil cannot hold you, so you will go inside that soil. That is quicksand condition. This part actually you can ignore, it is still confusing. Okay, this part you can ignore. Okay. So let us go to the next one. Yeah. So this problem is from our the from the chapter of consolidation. Okay. So 1 meter thick layer of saturated clay drained both faces at by 15 centimeter in 2 years. Okay. If a thin layer of pervious soil introduced in middle of the layer is then what will be the period during which the settlement of 15 centimeter will be completed. Okay, so normally what happens, and here 1 meter thick layer is there, saturated clay drained at both faces. So in that case 15 centimeter settlement takes 2 years. Now what we are doing is that we are introducing one more pervious layer in that soil. So due to that obviously our consolidation process will get accelerated, isn't it? So for the settlement of 15 centimeter lesser time should come. So we need to find out what is that time period. Okay, new time period. So how much is the new time period in which 15 centimeters? So initially what is there? So initially you have a 1 meter thick. Okay, so here also drainage is there. This is the drainage. Then what you're doing, you're introducing a pervious soil layer. Okay, very thin here. So what will happen? This layer will also like this will also act as, this will actually act as a drainage layer. So you're increasing the amount of drainage path. So for this reason what will happen, the consolidation will get accelerated. So water from here will come here, it will get exited somehow, and mm, water from this layer also will get here, flow along the drainage layer and will get exited. So these things are actually used in field regularly. Okay, some geosynthetic material are provided between. So when we do the filling, okay, say you're building something. So what we do, say you're building something, so what we do, say you first of all, say this is the subgrade. Okay, you put some geosynthetic material here, and here outside drains are there. Put some geosynthetic material, and then you put above that you put some soil. So what will happen, the water in this soil layer is actually flows along this geosynthetic material into the drains. So what you're doing, you're increasing the drainage, water drainage. You're giving the water more space to drain out, to accelerate the consolidation process. So the main task is to accelerate the process of consolidation. Okay, so consolidation, we studied the consolidation topic in detail, which is one of the most important topics. Consolidation, we also derived the 1D consolidation equation, all those things we derived. We saw that how time where learned about, we saw how actually consolidation take place, the void ratio reduces as effective stress increases, all those things we learned. Then we saw the consolidation test, 1D consolidation test, how to do that test. Then also we saw at the end, we saw how this time, the relation between time and consolidation, okay, using the time factor, all those things, all these things were derived from the 1D consolidation, one dimensional consolidation theorem, all those things we had studies. So this is actually related to that with this problem, right? So what was the relation between the time factor and all those things, if you can remember, what is this time factor? TV. HDR square. Okay. So HDR square is what? HDR square is our uh, drainage path length, right? So from here, see, these will be constant for the soil. Okay, this will be constant for that particular soil. This CV will be also be constant for that particular soil, right? And for a particular amount of settlement, say 50, this 15 centimeter settlement is say 50% settlement. Say, for example, we don't know how much, what is the ultimate settlement, so we cannot comment. Actually, say I'm saying, say this is 50%. So this TV is actually also constant. So TV is direct also related to the degree of consolidation, right? So here we are, so degree of consolidation in both the cases will be same, right? Because we need to find out the same degree of consolidation, that is for the same 15 centimeter settlement, how much time will be required if the drainage is actually increased. So degree of consolidation is the same in both the cases, so TV will be constant. So we can write from here T is proportional to HDR square, isn't it? You can write that. From here I can write this T1 by T2 is equal to HDR1 by HDR2 square, right? So now when this time is 2 years, when time is 2 years, what is my HDR? Yes, let us do that. It will exactly, it will reduce by 4 times. So when time is equal to 2 years, my HDR is 1 by 2. Okay, and when my time is, I don't know, my HDR is how much? 0.5 by 2, I think. Right. So what we are doing is that we need to find T2. So T2 is nothing but, sorry, T2 will be nothing but T1 by 4. So 2 by 4 to 2.5 years, right? So you are increasing the drainage, our time reduced from 2 years to 0.5 years. Okay, so that's why it's very important, in order to accelerate the process of consolidation, what we need to do is that we need to increase the drainage. Yes, time reduced by 4 times. All right. So if drainage path, so previously drainage path was this much, now drainage path is, so if, so we can, what we can write, if drainage path reduces by half, time reduces by how much? 4 times. By 4 times. So if drainage path reduces by half, my time reduces by 4 times. Okay. Okay. So this is the last problem that we'll be solving for this course today. So let us see, this problem is actually from our shear strength chapter, right? On the shear strength topic. So let us solve this problem. So a cylindrical specimen of dry sand was tested. In a triaxial test, failure occurred under a cell pressure of 1.2 kg per centimeter square and a vector stress of 4 kg. Find the angle made by the failure plane with the major principal axis. Angle made by the uh, plane of maximum shear stress with the major principal plane, shear stress on the failure plane, and normal stress on the failure plane. Okay, so let us do first, let us write the sigma 3. What is it? Sigma 3 is given 1.2 kg per centimeter square. Sigma d is right. So what will be sigma 1? Sigma 1 is sigma 3 plus sigma d, so 5.2 per centimeter square. Okay, now this is sand, right? So sand, so we can take c is equal to 0. So we have sigma 1 is equal to sigma 3 10 square 45 plus pi by 2. So c is 0. No, that part is not there. So from here, please find out phi. So what will be phi from here? Friction angle of the soil. It's 38 degrees, 38.6 degrees, I guess. Okay. So first is find the angle made by the failure plane with the major principal axis. Okay. If you remember, this is nothing but 45 plus pi by 2. It will be 64.35 degrees. Okay. Now angle made by the plane of maximum shear stress with the major principal axis. So we don't have to do anything. Can you tell me what should be this answer? The angle made by the plane of maximum shear stress with the major principal plane. So if I can draw the Moore circle once for you, see this not 90 degree. So this is the Moore circle. Where is the uh, where will be the maximum shear stress? Here, here. So this will be the angle. Just give me 1 second, okay? No, we need to find the angle. Yeah. So what will see this is my term x, right? This point circle, this radius, this diameter, this if this is the center, this is my radius, right? So this point. So what will be this angle? Yes, exactly 45. So the angle made by the plane of maximum shear stress is this 45 degree. Okay. So now at the end motor, so we need to find out shear stress on the failure plane and normal stress on the failure plane. For that we know this our general formula sigma 1 by sigma 3 by 2 then sine twice alpha. So you can find this out, and sigma is sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 alpha. Okay, alpha you already found out 64.35 degrees. right? So please calculate this tau and this sigma value. So this will come out as 1.56 kg per meter square. Okay. So with this actually we come to the end of this course. So I hope this course was beneficial to you. And at the end, I would like to thank all of you for attending the lectures and also the discussion sessions, also giving all the quizzes. Uh, and I also want to thank the other Ts of this course, which were Mr. Shiv Shankar Nandi and Mr. Gobindo Das. So they were also, so Mr. Gobindo Das was actually answering all your queries in the discussion forum, and also he was uh, correct handling on those assignments and all. And the other discussion session was you attended, that was by Mr. Shivshakar Nandi. So I'd like to thank them, and also I want to thank our course instructor, Professor Priyank Ghosh and NPTEL. So with this we come to the end of this course, and I hope all of you do well in the exam. So when is the exam? Okay, 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 okay. Okay, okay, okay. And cities, this exam city? Okay, okay. Okay, okay. On 29th. Okay, okay. uh, what mail came? I did not see. Where is that? Some mail came or what? Okay. Okay, okay. Then they might give maybe. I think they might give formula sheet then. Then there is a problem. That I'm not sure. Because generally in I. Uh, okay, okay. Oh, oh, okay, okay. Thank you. Yeah, yeah, yeah. Yeah, yeah, okay. Okay, okay, understand, understand. Yeah, yeah, yeah. Okay, okay. Thank you. Thanks a lot. Okay, okay. Thanks a lot. Yeah, yeah, yeah. Okay, okay. Okay, okay. That's a very great compliment. Okay, so are you planning to take more courses in the next session also? Okay, foundation engineering. Yes, that will be taken by I think Kaushik Dev sir from IIT Kharagpur. I think yeah, yeah. Okay. That course is also very good. Okay, okay. Okay, okay, okay. Okay, okay. Thanks a lot. So hope to meet you soon, sometime maybe in person, sometimes in future. Okay, 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 so yeah, yeah. So already we are connected in LinkedIn, so we will get like be in touch, and maybe in next course if we are there, so maybe that time also we can like interact. Okay, okay, okay. Thanks a lot. Thank you. Thank you. Have a good day. Okay. Thank you. Thank you.